NIS AI, Statistics and Data Science in Practice webinar series. So this is a monthly series that bring experts from academia and industry to explore the advances in AI. And today marks the first talk of our fall 2025 series. So the theme is on critical role of experimentation in the development and refinement of AI systems. So we will have 3 additional talks scheduled later in the semester. So please stay tuned. So before we start, so first I would like to thank Megan, Nancy, and Devi, and other NIS AI in Stats committee whose efforts make this webinar series possible. So the recording of the past events are available on NIS YouTube channel, and our speakers, including Professor Ramdas, has kindly allowed to share their slides, and which we are happy to provide if you reach out to us. A few reminder of the logistics. So for today's session, please enter your questions in the QA box. So I'll be monitoring them, and we will have 4 parts of the talks, and I will pass the question to Professor during these natural breaks. So we encourage you to engage actively. Okay. And now it's my great pleasure to introduce our speaker. So Professor Ramdas is an Associate Professor of Statistics and Machine Learning at CMU. And he has received lots of honors, including the Presidential Early Career Award, the Sloan Fellowship in Math, and SF Career Award, and the COPS Emerging Leader Award, and the IMS Peter Hall Early Career Award, and Bernoulli New Research Award, as well as some faculty award from the industry like Adobe and Google. And in addition to that, he's also a Cavalier Fellow of the National Academy of Sciences, a recent fellow in 2025, so a recent fellow of the IMS, and also named the Statistician of the Year by the SS Pittsburgh chapter. And will also serve as the program chair of the AI Stats 2026. All right, so without further ado, let's welcome Professor Ramdas, who will share with his recent work on sequential causal inference in exponential and the observational settings.
Great. Thank you very much, Will and Nis, for this invitation. I'm very excited to be here. Thanks, everyone, for joining. It's already a large and wonderful audience. I'm very excited to present this work to you all. So I have put up my slides. I just put them up on this website. I put it in the chat. If you want, you can follow along. It might help with some definitions if you want to refresh while the talk is going on. I'm just going to go ahead and share my screen. Okay, you should be able to see my screen now. And I will, there we go. Okay. Okay, so I will be talking about sequential causal inference today, which is a very central problem in many areas of modern applied AI. It turns out, like, whether you're doing multi-arm bandits, reinforcement learning, or now reinforcement learning with human feedback, things like that, you're often collecting this the data sequentially, and you're often peeking at the data as you go along. And we'll show you how you can do valid statistical inference using this new concept called asymptotic confidence sequences. Okay, if you like the contents of this talk, if you find them interesting, they're all related to this new concept called e-values. And so we have a new book, which I call the e-book on hypothesis testing with e-values. It's on my webpage, it's on archive, and it'll also be the inaugural issue of a new book series called Foundations and Trends in Statistics. So you'll find many more ideas in there. I'm going to talk about one narrow set of ideas around confidence sequences. Okay, I'm going to start by going back to maybe about 10 years or so to an infamous instance of what's called peaking at p-values. This is kind of just to motivate the problem setting and make you understand what the issues are and so on. And so there's something called the power posing controversy, and the two of the characters are Amy Cuddy and Dana Carney. They were authors on a paper in around 2012, a top psychology paper in which they claimed that before giving a talk like this one, if I went in private and I took on expansive or powerful poses, then I'll measurably give a better talk. And it was a big hit because many people fear public speaking, and so if they could do something to measurably improve their performance, that was a big deal. So it became a top 10 TED talk of all time, a New York Times bestseller book, and well-cited paper. And then people tried to reproduce these findings from many universities, and they started to be issues of reproducibility. Some things were reproducible, self-reported feelings of confidence, but most things, many of the other things were not consistently reproducible. And in 2014, Dana Carney retracted her name off the paper, and she's now at Haas Berkeley. And from her website, she put this PDF up on why she retracted her name. She said she doesn't believe in the results anymore. And one of the reasons she gave was, initially the primary decision variable of interest was risk taking. They kind of randomized things into people who did or didn't do power posing, things of that kind. And so they ran subjects in chunks and checked the effect along the way. It was like 25 subjects, then 10, then 7, then 5. Back then, this does not seem like p-hacking. It seemed like saving money and things like that. Okay, so essentially she points to some issue. And in classical statistics, it goes under the phrase of sampling to a foregone conclusion, but maybe not everyone's familiar. So let me just try to tell you what's really going on. So the problem with continuous monitoring is where you have an open-ended study. You don't know how much data you need in advance. So don't think about clinical trials where, like, say, the FDA has some oversight and you have to pre-register and pre-report everything, pre-decide things. Think about more the IT industry, where things are being deployed on a daily basis, and people are running experiments in the real world, and they don't pre-specify maximum sample size or times the budget. They kind of just be like, okay, let's see how this runs. It could be A/B tests, multi-arm banded tests, RL-based tests, policy-based tests, things like this. But essentially, they collect more data, and then they look at their data after some time, after a few hours, or after days or something like that. They look and see, is the p-value less than alpha? And if it is, then they stop and say, okay, that's great. I think I've rejected my null hypothesis as something to go, to discover. But if not, then they say, well, okay, let's just collect some more data. And it's this loop that's really a problem. So if we use commonly taught p-values that we learn in statistics, or we teach in 200 countries around the world, if you do this, which is what it's very tempting to do, because you're not explicitly taught not to do it, perhaps, then the false positive rate is going to be much larger than alpha. So even when there's no effect, you will reject the null of no effect. Now, formally, mathematically, what's going on? So let's say p superscript n for now is a classical p-value. Let's say a t-test p-value or something that you've calculated using the first n samples. Now, if this is really a valid p-value, then under the null hypothesis of no treatment effect, then the probability that pn is less than alpha should actually be less than alpha. Like pn should be uniformly distributed or stochastically larger than uniform. But now, if tau is the stopping time of the experiment, so often tau depends on the data. Tau could be the first time at which Pn was below alpha. Okay, so you're continuously monitoring Pn until Pn drops below alpha. Then P tau is not a valid p-value. So even if each Pn was a valid p-value, P tau is not a valid p-value. The probability that P tau is less than alpha is actually not less than alpha. In fact, it's usually equal to 1. Like for typical p-values, the stopping time will happen almost surely, and it's you will actually make a false positive with probability 1. Now, this is not special to p-values. People have, this is the problem with p-values. It's got nothing to do with p-values. You switch to confidence intervals, you have the same problem. So with confidence intervals, you'd be peaking and you'd be making a decision, let's say, based on whether the 1 minus alpha confidence interval for a treatment effect contained 0 or did not contain 0 or something of that kind. And so and you'd continue if it didn't, if it still included 0, you'd think, okay, maybe I need some more data or something of that kind. Again, like the false positive rate would be much larger than alpha. And the same kind of notation wise, if ln and un is a classical 1 minus alpha confidence interval, what it means to be a valid confidence interval for, let's say, a treatment effect theta is that, let's say, the probability that theta lies in ln un is at least 1 minus alpha. Okay, that's just the coverage statement. But if tau is the stopping time of the experiment, for example, you stop when the first time at which the lower confidence bound of your confidence interval is above 0. So this means that it looks like a positive effect. You stop at that time tau, then L tau U tau is not a valid confidence interval. So the probability that theta lies in L tau U tau is definitely not at least 1 minus alpha. It's actually usually equal to 0. Now, this is not just an issue in this power posing kind of setting that I said. It comes up in all kinds of places in science. So, for example, here's an experiment from a Large Hadron Collider physics. This is a University of Cambridge article from a few years ago. So they said, these are actually two different articles that I've pulled together, but the top one says the difference between the Large Hadron Collider result and the standard model of physics was about 3 sigma. However, to be really sure the effect is real, then more data is needed to reduce the experimental error. And then there's another article which says, well, today's result is around 2 sigma. That isn't conclusive on its own, but it does add further support to a growing pile of evidence. So it's the case in many sciences, definitely in psychology, neuroscience, even in biology, things like that, where you're somehow collecting data over time. The frequency of peaking might be infrequent or not. So like, for example, in physics, it's rather infrequent. Maybe they peak only, let's say, every 6 months or something like that. But in a psychology lab or a neuroscience lab, the peaking might be after every subject or something. There's nothing stopping the graduate students from analyzing the data after every subject is collected. And in the IT industry, it could be somewhere in between. Maybe it's every hour or every day or something of that kind. So not every subject and not every 6 months, somewhere in between. So the main thing about all of these, and also this occurs in meta-analysis of drug trials, the main thing about all of these is that there's some open-ended nature. We're not sure how much data is to be collected in advance, and there is a natural tendency to want to look and make these decisions, but now that invalidates statistical inference. So what we instead want, you can tell people don't do this. Okay, but they're going to do it anyway because there's an incentive to, because somehow fixed sample size statistics is very restrictive. It's very hard to decide ahead of time. I want exactly this much data, no more, no less. Okay, so instead we might want methods that legalize peaking, that allow you to peak. Okay, so we call these sequential anytime valid inference methods, or SAVI methods. So SAVI methods are those that do yield valid inference at arbitrary stopping times, possibly not specified or anticipated in advance. SAVI methods, if we could develop them, would allow for continuous monitoring and analysis of the data, adaptive decisions to halt or to continue experiments for any reason without violating the validity of the claims. Basically, it would provide a lot of flexibility to the statistician or the data analyst in industry. It would legalize peaking. And this is useful in many exploratory settings, especially those without explicit oversight. Okay, like university labs and tech industry don't have the FDA sitting over you, but in pharma industry, maybe you do have an FDA with oversight looking at exactly what you're doing, making sure that the statistics is rigorous. But in many other settings, people are doing statistics and data analysis in where there is not oversight, and the flexibility is then used and useful. Now, this SAVI method, for those who are familiar with standard sequential inference, it differs from Wald sequential inference. So Wald designed a single stopping time to trade off type 1 and type 2 errors at specified levels. Here, we're asking for valid inference at any stopping time, not specified in advance, arbitrary stopping time. So it's, there's a difference in perspective there. And SAVI can really be seen as an offshoot of what Robbins called power 1 tests. Okay, so at a very high level, like the inferential tools behind SAVI come in, there's 4, pieces of them. The left ones are just real valued measures of evidence. So p-values, but now the sequential analog of p-values are called anytime valid p-values or p-processes, and something called e-values or their sequential analog, which are called e-processes. These are just real valued measures of evidence. Now, on the right, there are measures of like uncertainty quantification associated with the level alpha. So the natural sequential analog of a confidence interval is a confidence sequence. It's a 1 minus alpha confidence sequence. And instead of a standard hypothesis test like a Neyman-Pearson test or something of that kind, you have a sequential test, a power 1 sequential test, and those are associated with the level alpha. So you can move between all of these objects, but today's talk will be about confidence sequences. The thing on the top right, that's what I'm going to focus on. Therefore, estimation, they're associated with the level. But if you are interested in testing, you can actually move between from confidence sequences to get anytime valid p-values or sequential tests, things of that kind. Okay, so now I'm going to tell you what confidence sequences are. There's a nice history to them and relatively modern work as well, which is interesting. But the key part that I'm going to get to is asymptotic confidence sequences, because this is where it really comes together with sequential causal inference, which is the third part of the talk. Okay, so I'm going to spend about 10 minutes on each of these, and then I'll wrap up with a more broader outlook about science. Okay, so what is a confidence sequence? A confidence sequence for a parameter theta is a sequence of confidence intervals, ln un, that are constructed, ln and un are constructed from the first n samples. But these confidence intervals have a uniform, or it's called a time uniform, or a simultaneous coverage guarantee over all of time. Okay, and so the statement looks like the probability that for all t simultaneously, theta, your quantity of interest, lies in LTUT, that probability is at least 1 minus alpha. Now, this definition goes back to essentially work by Robbins and a bunch of collaborators in the late 60s. This is much stronger than the usual pointwise or fixed sample confidence interval definitions that you're usually familiar with. It's subtle, but the for all is outside the probability. So you should read it as for all fixed sample sizes n, the probability that theta lies in ln un is at least 1 minus alpha. Okay, so that's the classical notion, and a confidence sequence moves the for all inside the probability. It's a simultaneous notion. It's a much stronger notion. Now, some implications, if you had a confidence sequence, then one of the implications is that you get valid inference at arbitrary stopping times. So I've now written the error notation, but then for any stopping time tau, the probability that theta does not lie in L tau U tau is at most alpha. So you do get coverage. L tau U tau is a valid confidence interval at stopping times if I started with a confidence sequence. Okay, you also get valid post hoc inference in hindsight. You can even ask questions at times that are not stopping times. I won't really dwell into that. But essentially, because of the simultaneity, I don't have to pre-specify the sample size. I can plan for a sample. I can still plan for a sample size, but I can stop earlier than that, or I can extend beyond that if I want to. Now, a key property is that actually these are all equivalent to each other. If I want inference at arbitrary stopping times, I effectively want a confidence sequence. So you can move between these definitions, like the three mathematical definitions that are on this slide. They're all equivalent. They all imply each other. Okay, so here's some examples, just so you have some expressions to think about. I'll show you some figures on the next slide. Okay, so suppose x1, x2, and so on are IID unit variance Gaussians. Okay, you want to estimate the mean. Or maybe they're just data that's bounded in -1 to 1. So they could be non-parametric, they could be just bounded in -1, 1, and you want to estimate the mean. Then this expression, let's look at the first expression. That is a confidence sequence for mu, the unknown mean mu. Now, it's kind of natural that it's centered at the sample mean. So the first part should not be surprising. It's the second part that's surprising, which is what is the width of this confidence sequence? Okay, so there are some small constants out there, and they are small, which is good. Like 1.7 is like √3, for example, something of that kind. Now, the pieces to pay attention to is the dependence on alpha. So the dependence on the error probability alpha is like log 1 over alpha. This is, or square root log 1 over alpha. And this is the same dependence as you get from the central limit theorem. The dependence on n, you see a 1 over square root of n, which also makes sense. But there's an additional log n in the numerator. So you should think about that log n as essentially the price of being simultaneous. Okay, this is like a non-asymptotic version of what's called the law of the iterated logarithm. If you have not heard of the law of the iterated logarithm, that's fine. This expression is a confidence sequence, but you can compute it explicitly. You can easily code this up, and this allows you to sequentially monitor your data. Now, the second expression is also a confidence sequence. You can take running intersections so that you only get a decreasing sequence. So that's because if the first expressions are all simultaneously valid, then so are the second set of intervals. So here's a figure, and this will help elucidate the trade-offs between confidence intervals and confidence sequences. So over here, let's focus on the left plot first. The true mean is 1. That's the gray dotted line. That's what I'm actually trying to cover. In this experiment, I know it, so I can plot it for you. Now, I have time on the x-axis in logarithmic scale, and the green dotted curve is a confidence interval. Let's say a central limit theorem type confidence interval. Okay, and the orange curve is a confidence sequence, like for example the one I showed you on the previous slide. Okay, so now the guarantees and the definitions are written just below in those equations. So the thing to notice is that a confidence sequence is wider than a confidence interval. It has to be. I'm giving you a stronger guarantee, so I have to pay a price for it. It's going to be wider. You can notice that it's not that much wider. It's like some constant factor, maybe about √2 times wider is basically some kind of reasonable number to keep in mind. The thing to notice with the confidence interval is that there are many times at which it's wrong. Okay, so for example, if you look at just after time 1000, there is a period in which it is entirely not covering 1, the true mean. So it's incorrect. There's another time just after that, another time just after that, and you can prove that this is not. I didn't just pick a lucky simulation. You can prove that in every single simulation, the confidence interval, the green confidence interval, will miscover infinitely often. It will infinitely often miscover 1. Okay, so that will happen almost surely in every run. But the confidence sequence guarantee is that with 95% probability, it will simultaneously cover 1 from time 1 to infinity continuously. Okay, so it's really like a confidence band around 1. Okay, so you can already see why a confidence sequence allows you to sequentially monitor. It doesn't kind of expect you to get lucky or unlucky. Nothing like that is going on. You have a simultaneous guarantee, but the green curve does not have a simultaneous guarantee, right? Now, on the right, so the left plot is a single run. I just ran it once and that's what came out. The right plot is plotting the cumulative miscoverage rate against time, but now running the left curve 10,000 times. I'm running 10,000 different experiments and I'm plotting, well, how many times do I miscover between 0 and t? Okay, and so with the confidence sequence, what you can see is that miscoverage rate is, in this case, alpha is 0.1. That's the gray dotted line. And the confidence sequence is going to reach 0.1 at infinity, essentially. It's basically saying between 1 and infinity, my miscoverage rate is 0.1, and it really uses up that alpha error budget between 0 and infinity. Now, you can tune this orange curve so that it uses up most of the error budget up to time 1,000 or 10,000. So the orange curve is entirely tunable. In this talk, maybe I won't talk about how to tune it, but you should think about the orange curve as being an alpha spending function that you can tune how you want it to go between 0 and 1. But in this case, there's some range. It's going between 0 and 1, between time 0 and infinity, from 0 to 0.1, I mean. But the green dotted curve is the confidence interval of CLT, which is basically, the way to read it is by time 1,000, in 30% of the experiments, it has miscovered. By time 10,000, in 60% of the experiments, it has miscovered. So that's what this is doing. And this green dotted curve is going to go to 1. Basically, in every single experiment, it will eventually miscover. It will not just miscover once, but it will miscover infinitely often. So anyway, hopefully that again visually brings out some trade-offs between confidence intervals and sequences. Now, you can't just construct confidence sequences for means. You can construct them for other interesting quantities of interest. So for example, you can construct them for quantiles. So here's an explicit expression for quantiles. I'm going to define this quantity ut that's very similar to before. So the way you should always read this is small constants, square root log t, square root log 1 over alpha divided by square root t. Okay, so the expression is always going to be very, of that rough form. And the claim is that for any distribution without any assumptions, it's just actually any totally ordered distribution with no assumptions. This is a confidence interval for the median. I'm going to take the empirical q of half is the quantile function at half, which is the median. And q hat of t is the empirical quantile function at time t. So I'm going to take the empirical quantile function at half minus ut and the empirical quantile function at half plus ut. And that forms a band around the true median, which is simultaneously valid from time 1 to infinity with probability 1 minus alpha. Okay, so this is a confidence sequence for the median. But you can also cover all quantiles simultaneously. So this is for a single quantile. I'm showing you an example. You can do it for other quantile levels too, not just a half, of course. But here's an example of an expression which is slightly different constants. But now it's simultaneous over both time and quantile level P. Okay, so basically it's saying that if I take the empirical quantile at P minus UT and the empirical quantile at P plus UT, it covers the true quantile at the Pth quantile simultaneously for all P and all T with probability at least 1 minus alpha. Okay, so pretty interpretable things. They work reasonably well in practice. So this is an example of what happens, let's say, with the Cauchy distribution. Here on the left, I'm only plotting the 0.9 quantile. So the gray solid line is the true 0.9 quantile. The black dotted line is the empirical 0.9 quantile. And the green curves are the confidence sequence for that 0.9 quantile. And of course, the confidence sequence is going to be asymmetric, but because I have less samples for the upper quantile than I have for the lower quantile, right? So it is asymmetric, and that's good, like in that it should be. And the right plot shows now when you do all quantiles simultaneously, these are like confidence sequences for the CDF effectively. And so you can see at 3 different times, 100,000 and 10,000, the confidence sequences for the CDF are getting tighter and tighter. Now, nothing specific about scalars. Okay, I talked about scalars like means and quantiles. Okay, you can do CDFs, you can do matrices, things like that. So if you want to do sequential covariance matrix estimation, you're getting more and more data over time. You want to track a covariance matrix and ask about how quickly does the empirical covariance matrix concentrate around the true covariance matrix and operator norm. So here now there's a few other things. So B is a bound on the size of the entries of X. D is the dimension of the matrix. N is the number of samples. And so you get an expression of this style uniformly uniformly over time over n. In this case, I'm calling size n instead of t, but uniformly over n with high probability. And so this is a visualization when d is 2, because when d is 2, you can visualize the covariance matrix as an ellipse. And then the orange plot is telling you like somehow the inner and the outer ellipses that trap the true ellipse with high probability. So the blue curve is effectively the true sigma. This is like, the larger and smaller singular values and the singular vectors. So you can visualize it as an ellipse. And so yeah, it works reasonably well. You can use this for tracking things over time. So here's a summary, okay, of there's been different statistical problems that could be of interest. So standard parametric inference. I just have a parametric family. I want to I want to estimate the parameter theta, things like that. Standard confidence intervals go back to Wald, Neyman, Fisher, things and so on. And more recently, we have developed fully general tools for confidence sequences for those parameters. Mean estimation in different settings where you have different kind of tail assumptions. It could be on bounded data or sub-Gaussian data, heavy tail data, things of this kind. You can do quantiles, you can do sampling without replacement. So there's been work on classical confidence intervals, and then there's been work on confidence sequences. So there's a lot of parallels. But now everything I've told you so far is entirely non-asymptotic. There's no asymptotics in my definitions or in my constructions, nothing. But in classical statistics, there is a huge role of the central limit theorem to construct asymptotic confidence intervals. And this is useful for problems where actually non-asymptotic inference is provably impossible, but asymptotic inference is actually possible. We use the central limit theorem as a tool everywhere. What is the analog of that in confidence sequence land? Is there an analog of the central limit theorem? The answer is yes, and that's what I'm going to tell you about next. Okay, so this was an annals paper last year, which is titled Time Uniform Central Limit Theory. So you should think of it as an extension of the central limit theorem to the time uniform setting, and asymptotic confidence sequences. Here's a definition of asymptotic confidence sequences, which is constructible and achievable and sensible. So I'm going to on the next slide define asymptotic confidence sequences, and show you why it's useful, and we'll get to sequential causal inference, which is especially in observational settings where you need to rely on asymptotics. There's no other way around it. But this is a good time to pause and see if there are any questions in the audience so far, and if not, I'll continue with the second part.
Yes, Professor. We do have lots of questions sent to us directly. So
Okay.
I would suggest the audience to ask questions through the QA box in the bottom so that everyone can see the question. Many people just send to me directly. The first question is, does it matter how exactly one decides to stop?
It does not matter. So like in terms of the validity guarantee, it does not matter. You can absolutely any stopping rule based on the data in any way or not based on the data, they all result in validity. But if you have a particular stopping rule in mind and you are going to stick to it no matter what, then it's possible then you don't need confidence sequences. It might be possible to derive confidence intervals that are valid just for that stopping rule. That is also an area of research and investigation. It's not easy for a typical stopping rule to do that, but sometimes it's possible. But for validity, these confidence sequences allow you to do arbitrary stopping. You don't even have to tell me when you finally report. You don't have to tell me why you chose a particular stopping rule. When you made that decision, you could have made that decision 100 steps in why you're going to stop and when and things like that. So, and none of it has to be reported. Your confidence interval will be valid.
Okay, I have 9 other questions.
Yeah.
How would you consider employing design principles when analyzing existing clinical trial or observation data that has already been collected?
Okay, let's get to the observational data stuff first. That's in the third part of the talk, and maybe then it'll be easier to revisit that question.
Okay, is there a production version of the sequential causal model for A/B test?
Is there a what version?
A production version.
Yeah, so I will talk about, again, so maybe a lot of these questions will get answered in the third part of the talk, and in some examples I'll give of people who have deployed this in production.
Okay, how does this apply with RL and probabilistic graphic models?
In reinforcement learning, we are constantly taking actions and collecting data sequentially. You can construct confidence sequences for the value of a particular policy. In fact, we have particular papers that construct both on policy and off policy estimates of value. So what off policy estimation is I'm running a particular policy in practice and I want to ask a counterfactual question. Well, what would my reward estimates have been had I run a different policy? That's called off policy. I never ran the policy. So you can do sequential off policy estimation, which means as you're running one policy in deployment, you can construct a confidence sequence for the value both of the policy that you're running and for another policy that you're not running. And so you can do a kind of a gated deployment where as soon as one confidence sequence is clearly better than the other one, you can switch which is the policy being deployed and the policy which is not being deployed. So you can switch them. So all of this stuff does apply immediately to bandit and RL settings. I will not be discussing them in this talk just because the notation will start to get extremely complicated. So I'll focus more on slightly simpler settings, but we have papers which extend them to more general settings.
Yeah, there are quite a few questions about causal inference because I see on the third part you want
Yeah.
this causal inference.
Okay, so maybe I'll take the causal inference questions after getting to that part.
Yes, yes. There's one additional question. It seems that the traditional confidence interval controls FDR, whereas the CS controls FWER. Is this true?
I mean, you can think of it like that. That is a reasonable way to think about it. It somehow there are no different hypotheses. Like when we think about FWER or FDR, we are really thinking about many different hypotheses. Here, there isn't. It's the same quantity of interest in some sense, but yes, that is a reasonable analogy. That confidence intervals, when I run a single experiment over time, 95% of those confidence intervals I should expect to cover, and 5% of those intervals will not cover. The problem is I might stop at a particular stopping rule that picks out those 5% that don't cover. And a confidence sequence is like asking everything to cover. So that's a reasonable analogy.
Okay, great. Thanks. So I will keep the
Yeah.
talk moves on. And if for questions that has not been answered, feel free to type in the Q&A session later part. Thank you.
Sounds good. Thanks. So now I'm going to define asymptotic confidence sequences, which is what will enable sequential causal inference. Okay. So here's the definition of an AsympCS, and it's a very non-trivial definition. So let's just pay attention to it. Now I'm focusing on mean estimation, and I'll tell you later on how to generalize this using the delta method for general semi-parametric inference problems. But for now, let's say I'm interested in estimating a mean. So now I'm going to estimate it using a sample mean mu hat t. So mu hat t is just a sample mean, and plus or minus b bar t. Now b bar t is the thing of interest. That's the width that I'm actually interested in. Okay, so I'm going to call this sequence a 1 minus alpha asymptotic for mu if there exists a non-asymptotic 1 minus alpha confidence sequence for mu, and that's going to be given by b bar star t. Now the star is supposed to represent some kind of oracle knowledge. You don't know it. There exists some non-asymptotic confidence sequence, and your b bar t is an almost sure approximation to b bar star t. Now the bar is supposed to represent uniform. It'll come relevant to the next slide. I'm using the bar to represent uniform and the star to represent an oracle. So the thing you construct is in blue. That thing is an asymptotic if there is some other oracle red quantity which maybe you can't construct, but you can prove mathematically that your blue one is an almost sure approximation to the red one. Okay, so that's kind of a subtle definition. So in English, an asymptotic is an arbitrarily precise, almost sure approximation to a non-asymptotic, a standard CS for large enough t. Now, I've shown you how to construct confidence sequences non-asymptotically in the previous part of the talk. And now I'm going to tell you how to construct asymptotic confidence sequences. But first, I want to motivate why is this definition sensible? This is not how we typically define asymptotic confidence intervals, but actually it's very closely related. Okay, so think about the classic CLT-based asymptotic confidence interval. It looks like this. Mu hat n, I usually use n if it's a fixed sample size. And the dot here represents, again, it's a point-wise interval. There's nothing uniform about it. So b dot n. Okay, here now b dot n is some kind of, let's say, sample standard deviation. Phi is the Gaussian CDF. So phi of 1 minus alpha by 2 divided by root n. This is the standard. Hopefully everybody has seen this like a million times. It turns out that when you are invoking the CLT to justify that this is actually a valid confidence interval, a valid asymptotic confidence interval, it turns out that in the background, there is a non-asymptotic confidence interval b dot star n that you cannot construct, such that the thing you do construct, b dot n in this expression, is an improbability, a consistent estimate of b dot star n. It turns out this is true. This is we don't teach this, but if you think about, we have it explicit in the paper, but if you think about when you write down the proof, what's really going on in the background of the proof is we are basically saying there's something we can't construct, and this b dot n which we can construct is an in-probability approximation. That's really underlying the invocation of the CLT. So in contrast, our definition of asymptotic requires that this B bar star T is not an in-probability approximation, but an almost sure approximation, because it's kind of a stronger guarantee. So it kind of requires a stronger notion of convergence. I could have defined asymptotic confidence intervals in the same fashion. So you should think of the asymptotic confidence sequences as being a natural generalization of asymptotic confidence intervals when defined this way. Now here's a theorem, okay? This you should think of as the central limit theorem for the sequential setting, the time uniform central limit theorem. It's going to hold under exactly the same assumptions as the CLT. I only need a finite mean and variance, okay? So let's say I'm getting data from a distribution P with mean mu and finite variance. I don't know the mean or the variance, okay? Then I'll tell you about the role of this constant later. There's a constant rho for any chosen constant rho. This expression is an asymptotic. Okay, so let's look at this expression. For now, think of rho as 1, just so you can ignore what its role is for now. Okay, we'll talk about tuning it on the next slide. So mu hat t is the sample mean. That makes sense. Sigma hat t is the same standard deviation as you'd use in the CLT. Now, under the square root is things that are familiar. So the first term is 2t by t squared. Okay, so it's basically like 1 over square root t. Then you have a square root log 1 over alpha. And now you have a log t. Okay, and earlier it was log t, now it's log t. But you can construct expressions like this that are actually log t as well. Okay, so the log t versus log t is not fundamental. It's just for ease of expression. There are variants of this with log t. So now I've stated this theorem for the IID case, but the paper also has Lindenberg-Levy versions of this, which are non-IID or martingale versions of this asymptotic. Okay, so it's kind of interesting that every time we invoke the CLT to construct a confidence interval, we could instead invoke the time uniform CLT and get a confidence sequence. Not a standard confidence sequence, but an asymptotic confidence sequence. That's what this theorem is telling you. It's extremely powerful because it's extremely general. It holds under the same assumptions as the CLT holds. So now I want to tell you a little bit about rho, how to choose rho. Okay. And this is going to come into how, when do you initially start peaking at your confidence sequence? So remember that because it's an asymptotic confidence sequence, somehow the asymptotics have to kick in, right? So you don't want to peak too early at the confidence sequence. Like in a non-asymptotic confidence sequence, you could peak from time 1 to infinity. But in an asymptotic confidence sequence, you're going to peak at it from time m to infinity. So m over here is like the initial peaking time, okay? And if you look at the bottom expression, the guarantee is going to be that this is the coverage. This is what the analog to the limiting coverage guarantee. The usual limiting coverage guarantee does not have the for all t. It just says I can, the lim as m goes to infinity, the probability of coverage is 1 minus alpha. That's the limiting coverage statement of a confidence interval, asymptotic confidence interval. Now it's the same statement, but now I'm saying it for all t greater than or equal to m. So m is like an initial time. Now, when you are looking at it from time m onwards, you don't want to spend any of your alpha before time m. So what this rho m choice is doing is it's basically tuning the confidence sequence or tuning the asymptotic confidence sequence so that the alpha spending function is really between time m and infinity. So that's what this choice of rho m, it looks a bit weird, some log 1 over alpha divided by m log m, that's what it looks like. But its role is basically so that you don't waste your error budget before time m. Okay, so you really use it after time m. Okay, so in words, as you start at time m later and later, the time uniform type 1 error approaches alpha. You could have actually defined asymptotic confidence sequences this way, but it turns out like with confidence intervals, you can define them both ways and they're equivalent, and same over here, you can define them both ways and go back and forth between them. So just as a summary slide, the first two lines are what we think of as coverage guarantees for asymptotic confidence intervals. As m goes to infinity, the probability of coverage is 1 minus alpha. And it's the same thing for asymptotic confidence sequence, except it's for all t greater than or equal to m. So not just at time m, but from time m onwards. Okay, and so you can write it as coverage or miscoverage. And so I've just written it both ways for ease of understanding. Okay, so that's the definition of an asymptotic confidence sequence, and I showed you an example of it explicitly. It's like the central limit theorem, so it's a universal expression. There's no 100 expressions, there's really one expression. And now we're going to talk about how it's applicable to sequential causal inference. So you should think about this as being what I'm going to show you is how to do doubly robust causal inference in sequential settings at stopping times. Okay, and this is another way of saying it's like Robbins meets Robbins. The Robbins on the left with two B's invented confidence sequences, right? It was his definition, and he worked on it a lot for 5 to 10 years with his collaborators and students. And the Robbins on the right with one B less was a primary driver of semi-parametric inference. One example being what we call now doubly robust causal inference and so on. So what's coming up is really how to integrate the two Robbinses together. So here's a very simple setup. So let's say you're observing xt, at, yt from some distribution p, and we're usually interested in a causal quantity. I'm not. This is not a causal inference talk fully. So usually I would have prefer to write it in do notation and so on, or using a potential outcomes notation. But under some what are called standard statistical assumptions, consistency and no observed confounders and so on, this effectively reduces to estimating a statistical quantity, which is a difference of two conditional means: the expected value of y given a is equal to 1 and the expected value of y given a equal to 0. So in this setup, think of x as being some covariates like age, gender, things of that kind. A is a treatment level like 0 or 1, and y is an outcome of interest. So it could be a binary outcome or a real valued outcome of interest. And then psi is our usual, after making certain statistical assumptions, this is our the quantity that represents the average treatment effect that we're interested in. Okay, so let's say psi is our estimate of interest. Now, I'm not going to go into what doubly robust estimation is immediately, but there is a classical estimator for this problem. So you want to estimate psi, the average treatment effect. There's something called the augmented inverse probability weighted estimator, AIPW for short. Okay, and it looks like a sample mean. That's all you need to know for the moment, that the psi hat t, your estimate of the average treatment effect at any point in time, looks like a sample mean. Okay, and it's a sample mean of quantities f hat t, which is a function of all the data that you've seen so far from 1 to t. Now, what is this f hat t? I've not written down the expression explicitly, but f hat t involves estimating, or by estimating, I mean running 3 regressions. Okay, I'm calling them mu hat 1t, mu hat 0t, and pi hat t. Mu hat 1t is the expected value of y given x for the treated when a is 1. Mu hat 0t is the expected value of y given x for the controls when a is 0. And pi hat t is an estimate of the expected value of a given x, which is called the propensity score. That is what's the probability of assigning a particular person to treatment or control. Of course, in a randomized trial, you know pi of x. You assign people to treatment or control. In an observational study, you don't know pi of x. You have to estimate it from the data. So that's what I'm calling pi hat. So you run basically 3 regressions. Pi hat is just like a standard logistic regression. Mu hat 0 and mu hat 1 could use things like random forests or things like that, depending on what you're estimating, whether it's real or binary things. And then you plug those into this f hat, whose expression I haven't written down, but it's a very simple expression. And psi hat t is basically a sample mean. Now, how do you learn this mu hat t? It's kind of important. We propose something called sequential sample splitting. Okay, and I'll tell you what sequential cross-fitting is soon enough. But what sequential sample splitting is as I'm observing the data, xt, at, yt, I'm just summarizing that into a single notation, zt. As I'm observing the data sequentially, I kind of split it into 2 parts, which I call the training piece and the evaluation piece. And now the training piece, I'm going to learn these 3 functions, mu hat 1, mu hat 0, and pi hat, only on the training piece. And then on the evaluation piece, I have unseen data. When I evaluate this function f hat, which uses mu hat and pi hat, I evaluate f hat on the z's which are in the evaluation set. So that's what the arrows represent, is that you learn using one part and that informs the function f hat, and you evaluate the function f hat on the other part of the data. Okay, so this gives you a sample split estimate of your average treatment effect, and it's a sequential sample split. Every time a sample comes in, you put it in one or the other. But now sample splitting causes a loss of efficiency, so you do something called cross-fitting, which is you swap the roles of the training and evaluation set, and you also simultaneously kind of in parallel learn mu hat and pi hat on the evaluation set and evaluate it on the training set. So you just swap the roles of the two sets. You get another sample split estimate with the two data sets swapped, and you average these two sample split estimates to obtain what's called the cross-fit estimate. So this is what I call sequential cross-fitting, and that's going to be represented by psi hat cross t. The main important thing about psi hat cross t is it's very easy to kind of do online. You can do online updates to all of these functions. You can calculate them online, and they're just sample averages at the end of the day. Okay. So here's the final theorem that you get is an asymptotic confidence sequence for the average treatment effect in an observational setting for a trial that you're just observing. You're not actually randomizing. Okay. So you're just observing XT, AT, YT from some distribution P. So the assignments are being chosen in some sense by the participants, or they're by some mechanism you don't know. So we're going to construct a sequentially cross-fit estimator like I showed on the previous slide, and that's denoted psi hat cross T. Now here's what we call the doubly robust assumption. We assume that the product of the two errors of the mu hat, how accurately I estimate mu hat and how accurately I estimate pi hat, the product of the two errors is small o of square root log t by t. And we'll talk about this assumption a little bit soon, but assume that I can estimate these functions, the propensity scores and the regression functions reasonably accurately. Then this expression that I've written down, which is very similar to what you've seen before, is an asymptotic confidence sequence for the average treatment effect psi that I'm actually interested in. So it's centered at psi hat cross t as you saw, and its width is as you've seen before. There's a sample standard deviation log 1 over alpha, 1 over square root t, and a log t, or you could have also a log t version of this. Okay, so very clean. So the thing to remember is this is a setting in which there is no non-asymptotic confidence interval or non-asymptotic confidence sequence you can construct. So we must rely on asymptotics. In the classical literature, people have constructed confidence intervals for the average treatment effect. And the typical assumption there is that this product of errors is small op of 1 over root t. And our assumption is that the product of errors is small o, which is small o almost surely, of square root log t over t. So they're very similar, but they're actually incomparable. The probability, the improbability convergence is weaker, but the rate 1 over root t is stronger. Okay, and the almost sure is stronger for us, but we can do it at a weaker rate of square root log t over t. So it's a minor technical difference. I don't know of any practical setting where one is achievable and the other is not. So I mean, in practice, I think what the takeaway message is, when you can do doubly robust inference to construct confidence intervals for the average treatment effect, you can also do doubly robust sequential inference and construct confidence sequences for the average treatment effect. Okay, of course, this also applies to randomized experiments. In randomized experiments, you can still learn pi hat if you want to, or pi hat. You can set pi hat equal to pi because you know pi, in which case the assumption is trivially true. And so you can do this for randomized experiments as well. So here's an example on randomized experiments. So I think it's a well-known takeaway message, but when you're doing randomized experiments, doing regression adjustment with better regression estimators is going to yield tighter inference. But no matter what regression estimator you use, it's always going to be valid. Validity is actually not going to be in question. So here, this is a setting where the true average treatment effect is in dotted gray line. It's 1. And the green dotted line is what's called the unadjusted estimator. It's actually just the difference in sample means between the treatment group and the control group. I'm not doing any regression adjustment. Okay, so the green dotted line is I form a confidence sequence around that trivial quantity, and it's wide, but it's valid. And then if I do a regression adjustment using a parametric method, I get slightly tighter ones in blue. And if I use basically like online stacking or a super learner, things like that, and I get some even tighter, which is red. This is a randomized experiment. But if I move to observational studies, unadjusted estimators are just inconsistent. There's a bias, the bias caused by, what was the mechanism of treatment assignment, which I didn't adjust for. And if I don't correct for the bias, I'm just covering some other quantity. So the unadjusted estimator, which is basically based on a difference in samples means of treated and control, is just incorrect. That's the green curve. If I do regression adjustment and try to learn the propensity score, but I use only parametric methods that are just not rich enough, then the doubly robust assumption is not going to be true. I'm not going to consistently learn those quantities. And so, basically the product of errors may not go to 0, in which case I'm shorter, but I'm still covering the wrong quantity. There's asymptotic bias I cannot get rid of. But if I use powerful enough, this is where modern AI tools might be used. You might use deep learning based estimators if your feature spaces are rich enough. You could be using random forest, things like that. They're effectively rich functions that you could be doing rich non-parametric regression. If you're able to get rid of that asymptotic bias, then you'll get not only shorter intervals, but you'll also have removed the bias, and so that you're actually getting an asymptotic for the true quantity, the actual average treatment effect. Now, I've presented things here in the IID setting, but I hinted that we have asymptotic results for non-IID settings as well. So I just do want to point out that if you have time varying treatment effects, you can still run this stuff, in which case the quantity that you are covering is the average treatment effect of the people who have entered the study so far. You're just observing a study over time. There might be covariate shift and concept shift. The average treatment effect itself might be shifting over time. So that's what I've plotted in the dotted gray line. It's now called psi tilde t, where the tilde is supposed to represent that like a quantity that's varying. And yeah, so if you adjust appropriately do regression adjustment appropriately, you might want to use time varying regression, things like that. So tools from time series analysis would be useful here. But if you do that reasonably, then the asymptotic will actually, whenever you should think about it is whenever you trusted your asymptotic confidence interval, in the same settings, you should trust the asymptotic confidence sequence. And now I've focused over here on sample means, but the paper has a delta method, like the standard classical delta method, to extend all of these bounds to anything that has what we call asymptotically linear estimators. Okay, so this includes like pretty general semi-parametric estimation problems, many types of Z estimation and M estimation problems. So there's, essentially, when does the CLT apply? The rough answer is, well, kind of when things are asymptotically linear, then the CLT applies. Well, the same thing applies here too. So it really, even though I focused on average treatment effect and particular psi functions, you can extend this to pretty almost any time you can do confidence intervals for psi. You can also do confidence sequences for psi. Okay, so this has been applied in practice. So here are three different kind of success stories. So in a very different setting from what I've presented, the state of the art post-election audits. So this is like, democracy, things like that. So post-election audits are now based on betting for sampling without replacement for confidence sequences, or the dual, which is sequential tests for sampling without replacement. And so Philip Stark at Berkeley has been pioneering these, and some of these have already kind of been piloted in practice and so on. So these actually do work super well in practice. Right now, today, A/B tests based on these ideas are being used by Amazon and Netflix in public-facing software. So we were actually not involved with these deployments. They found our work, they implemented it, they found it works well. They're deploying it in public-facing products and software. And I mean, I think Netflix even has a blog post in which they mention how they use confidence sequences within their production development system. So right now, every change that's made by a Netflix engineer before it is launched to the entire world is, they'll do an internal canary testing pipeline on a small amount of the traffic. They'll, check many metrics that everything's working out okay before they actually launch. And those internal canary testing pipeline things use our, I think, quantile confidence sequences internally. And they've developed some of their own confidence sequences as well. And similarly for, as I mentioned previously, on and off policy evaluation, which are more Bandit or RL type setups, they're being deployed at Adobe and Microsoft again in public facing software. So many of these we were not involved in, and people found it useful. So I have some in my slides, some links to this is directly taken from the Adobe website about what they do and how they do it in their products. I found a Y Combinator startup. They didn't tell us about it. We don't know them. I found some. It's called Growth Book. They found our work. They seemed to like it, and then they deployed it, and it seems to work well. So I think the things I've presented to you are actually practical, and I encourage you to actually think about them and try them out. Now I would usually have paused here to take questions. So maybe I'll pause and take 2 or 3 questions before I kind of I want 5 minutes to summarize at a more high level as well. So maybe I can take some of those questions now.
Okay, great. I think, yeah, we have 3 questions. So the first question, if we have non-asymptotic CS, why do we need asymptotic CS?
Okay, let me answer again. There are many problems for which non-asymptotic inference is impossible. It's provably impossible. Okay. And doubly robust causal inference is a setup like that, where the bias only vanishes asymptotically. And there is no way, forget about confidence sequences, even for confidence intervals, there is no way in an observational study to construct a non-asymptotically valid confidence interval for the average treatment effect. We must rely on asymptotics. So confidence sequences, it's the same story. There's many problems. Doubly robust causal inference is one of them, but there's many other settings in which non-asymptotic inference is just not possible, meaning there is no non-trivial non-asymptotic confidence interval or non-asymptotic confidence sequence. Okay, so whenever you can do one, you can do the other. If you can construct a non-asymptotic confidence interval, you can construct a non-asymptotic confidence sequence. But when you can't construct either, these tools are relevant.
Okay. Next question. How to use confidence sequence to decide when to stop if there's no hope of rejecting H null?
Yeah, so the entire point is, if there is a null effect, if you're looking at a study in which the average treatment effect is actually zero, then you don't want the experiment to stop on its own, meaning the confidence sequence will always contain zero. It is up to you to realize I mean, it's looking like, I mean, you have to decide what kind of effect size is kind of small enough to be relevant for you. Once the width of the confidence sequence, so suppose the width of the confidence sequence falls below your interesting effect size, you can stop. So for example, suppose you only want to detect effect sizes, like let's say, which are 0.1 or larger, and your current confidence sequence is minus 0.02 to plus 0.04 or something like that, then its width is already smaller than 0.1. It is, and it includes zero currently. You can stop. You're not going to discover an effect of larger than 0.1 after this point, right? You can only discover an effect which is a subset of this. So if it eventually excludes zero, it might become 0.01 to 0.03, but that's maybe too, the effect size of 0.02 or something is too small for you to be of interest, so you choose to stop. So we don't specify the stopping rule. That is the entire point of this, is that the theory allows you to stop at any time. The practitioner chooses why they want to stop. Did they run out of money? Is the effect size too small? Or whatever. Their boss told them to stop, whatever it might be. The reason you choose to stop is entirely up to you. And that is the point, is to give you the flexibility of peeking at your data and deciding when to stop adaptively. You don't tell me ahead of time why you need to. So it enables peaking, but it does not enforce you to stop a particular way. You can stop whichever way. That decision is left to the data scientist.
Great, great. We do have three other questions. Do you want to answer here or leave to the end?
Yeah, maybe I'll take them. Maybe I'll take them at the end. Yeah,
And then,
I
okay,
have a few more slides, and then I want to back off a little bit.
okay, please.
So I think an interesting model for science, though, as conducted in the IT industry, pharma, or in universities, things like that, is not just one sequential experiment. What I told you so far is one sequential experiment, but what's really going on is that we have a sequence of sequential experiments. So as time passes, whether let's say you're in Amazon or something of that kind, employees are running more and more and more new experiments. Older experiments are stopping and newer experiments are being run. And this is going on forever. Each of these experiments could be short or long, and maybe the length of the time is not decided. And the number of experiments is really unlimited, in the sense of it's not like tomorrow they're going to ever stop doing those experiments. So it's like, as long as Amazon exists, basically they're going to run experiments. They run hundreds of new experiments per day. Okay, so it's like this is a small plot. What you should think of is many, many, many more lines. So these could be A/B tests that they're running. They could be what are called platform trials, in which you're trying out different treatments, but there's actually a common control population that's going on. Doesn't matter what the exact form of the experiment is. There is an interesting problem, which is not just within each experiment, like I discussed, but across experiments. So if you're trying to make discoveries, interesting discoveries across experiments, one natural question is, if I give you an infinite sequence of tests, let's say p-values, I'm switching from the estimation perspective to the testing perspective, because you can go back and forth between them. Is it possible to control the false discovery rate in a fully online fashion? So I have some initial p-value, the first p-value for the first experiment that I see at, let's say this is at the stopping time. I have a anytime valid p-value. At the stopping time, I ask, okay, is it less than alpha 1? The second test, when it stops, I ask, is it less than alpha 2? And so on. And how do I set these alphas so that at any point in time t, the false discovery rate up to time t is at most alpha. Okay, this is an online analog of in the usual multiple testing question, the number of hypotheses are fixed, the number of experiments is fixed. I do one shot. But here what I want is I want to continually make discoveries as I go along, and I have no idea how long the stream is. The stream is potentially infinite, and the decisions to reject are irrevocable. So you should think about it as, if you reject a null, it means I'm going to deploy a change to the system, or I'm going to go ahead with the next phase of a clinical trial or something of that kind. So a rejection is not revocable in the future. Okay, so how do you construct these online analogs of these classical multiple testing procedures? Offline FDR methods don't yield this guarantee. So at a high level, the picture looks like this. You start off with an FDR budget of alpha, and you basically assign alpha budget to each experiment. And as you run more experiments, the experiments use up your alpha budget. Now, this looks a lot like family-wise error rate control or union bound, but the difference is that if you make a discovery at some step, you find some confidence interval for the average treatment effect that does not contain zero, or you reject some null and you want to, you proclaim a discovery, then you actually earn back alpha wealth. You actually get back alpha wealth, which you can then spend on future tests. So this is actually an infinite process in which your alpha budget keeps shrinking and expanding. So I'm not giving you an explicit algorithm because there's several in the literature. I'll just kind of tell you at a high level, this is how things went. Like Foster and Stein, maybe 15, 20 years ago, kind of conceptualized this idea and designed the first alpha investing algorithm. And Aharoni and Rosset generalized this idea. Javanmad and Montanari created what's called the Lord algorithm, maybe 8 years ago. But then since then, they've been, our group has come up with several extensions. So LORD actually can be uniformly improved to what's called LORD++, a uniform improvement of LORD while still giving FTR control. And then you have variants that can adapt to null proportion and things like that. And most recently, we finally have like what we call an online analog of the Benjamini-Hochberg procedure, or the E-Benjamini-Hochberg procedure, that allows you to actually retroactively make some what are called accept to reject changes. You can never go from reject to accept, but you can go from accept to reject in hindsight. So if you're interested in this, there's several very simple algorithms to implement which allow you to control the FTR in an online fashion. This is what it roughly looks like across experiments. So you have really like one online FDR procedure that kind of goes across all experiments across all time. And each experiment J, this I that's over here at the bottom of the page, is supposed to mean you can look at it. You are allowed to peek at the experiment. Could be an A/B test, could be a multi-arm bandit experiment. You can peek at it continuously because you're using confidence sequences or their dual objects, which are anytime valid p-values. And then if you do reject the null, then that rejection tells the online FDR procedure, okay, now you have more wealth to spend on future experiments. And so each experiment is like a block that you can continuously monitor. And the whole thing there's an FDR. So you have a guarantee within each experiment of continuous monitoring, and you have a guarantee across experiments that you have FDR control at any stopping time as well. Okay, so here's the summary. Confidence sequences are sequences of confidence intervals that are valid at arbitrary stopping times. Sequential estimation and testing are actually dual problems. All confidence sequences are actually obtained by inverting sequential tests. So you can go back and forth between them. I focused on estimation, but if you want to do testing, these tools apply equally well to testing. You can construct tight confidence sequences even in non-parametric settings. Time uniform CLTs and asymptotic confidence sequences allow for sequential doubly robust causal inference in observational settings, and more generally for sequential semi-parametrics. And you can combine these with online false discovery rate or false coverage rate tools to control for peaking both within experiments and across experiments. So you have a very modular framework that allows the data scientist a lot of flexibility in design in changing different pieces of this modular framework. Okay, I'll stop there. I just want to thank my many collaborators over the years. You'll have the slides later on the website. I have references as well. I won't bore you with them. I'll stop at this page and take the remaining questions. Thank you.
All right, thanks, Professor M. That's a very, very nice talk. We do have lots of questions in the Q&A session or in the chart. So can this be extended to multiple treatments?
Yes, it can be. We haven't written that out explicitly, but there's nothing stopping it. So the answer to almost any of your questions could be could you extend it in a fixed n setting to multiple treatments? If your answer is yes there, then the answer is yes here. So you should really, it's almost like a reduction tool. Under almost the same assumptions that you could do fixed n inference, you can now do time uniform or sequential inference. That's the point of it, is to be that general. So we haven't written it down for every single particular case. There's 100-year-old literature on using the CLT for inference in 1,000 different settings. We have given the tools so that you can easily transform any of those settings from a fixed n setting to a sequential setting.
Yeah, that makes sense. And to what extent has a phrase like spanning alpha spanning alpha being superseded by Bayesian methods?
That's a great question. Everything in my talk is frequentist. The guarantees for confidence sequence are frequentist. The online FDR control guarantees are frequentist. So I'm in a fully frequentist setup. That's just a choice. But yeah, there could be Bayesian analogs of both of these. I'm not familiar to what extent they've been developed or deployed. I'm not familiar with either much of their development or their deployment. So, but maybe it's an interesting direction to explore. My preference is actually the middle ground. I think that there is a rich a space for empirical Bayesian methods where we are or maybe another thing is there's another term nowadays called frequentist assisted by Bayes. When you're running multiple experiments, you can share information across experiments. In fact, e-values have a natural extension to empirical Bayes, which is called compound e-values. So I have a recent paper on compound e-values, which uses empirical Bayes to construct e-values for many experiments simultaneously. This has not been fully, it's a very kind of new idea in the, let's say in the confidence sequence or in the e-value land. Of course, there's a very rich theory on empirical Bayes outside of that. But I think bringing the empirical Bayes to this literature, I think is very exciting avenue for future work. That's my preference compared to going full Bayes.
Okay. Can you elaborate on the particular importance of cross-fitting technique in the proof of the theory?
Yeah, absolutely. So it's just statistical efficiency. So if you do sequential sample splitting, you'll get valid intervals. They'll just be slightly wider. You should think of losing a square root 2 factor in n. It's as if your n is like n over 2 or something like that. So you'll lose a small factor. It's slightly inefficient. But when you do cross-fitting, you lose no factor. So like the expression that you get, it is asymptotically efficient. So it's meaning it is the minimum variance asymptotically that is achievable. So it's basically a statistical efficiency gain that you get by the sequential cross-fitting.
Okay. Do you have any suggestion for sequential computing will handle high-dimensional data without overfitting or leak over time?
Yeah, great question. I guess everything over here is focused on inference of particular parameters. It's not focused on prediction. So like, I guess the question might have been like, if I'm training a lasso or something like that, but maybe I'm using it for prediction. So I guess maybe we should talk about, am I interested in inference? If I'm interested in inference for the model parameters, then now there's, as we know for the lasso, even in the standard confidence interval case, there's many questions of what am I interested in? Do I want a confidence interval for every parameter, or do I want a confidence interval only for certain subset of selected parameters? And so the kind of the literature bifurcates in different ways in terms of the debiased lasso gives you confidence interval for every parameter, but certain other methods might select parameters and so on. So there's a rich, let's say array of methods. You can, I think, develop analogs of those methods for confidence sequences where you're repeatedly running the lasso at each step and you're choosing a subset of the parameters and you're constructing confidence sequence for the selected parameters. I think there's many technical subtleties. It has not been done. I think it's not trivial, but I don't see any fundamental bottleneck to, let's say putting some effort into developing those if that's of interest.
Yeah, thanks. We do have a few questions that were sent to me privately.
Yeah, go ahead. Yeah.
Since it works for any stopping rule, are there issues with the power?
Yeah, so I mean, I think that the easiest way to address the power issue is to go back to the original. Let's see if I can go back to the original figure. So this is I mean, it's very hard to visualize power, right? I mean, the power, I guess, depends on the exact setup, the signal strength, and things of that kind, it's easier to visualize confidence sequences. So rather than thinking in terms of the testing perspective, it's easier to visualize in terms of the estimation perspective. This is the price to pay. Visually, you see the price to pay. You are getting a wider confidence interval, but all I can say is that you have, like, it's not that much wider. Like if you look at it visually, it's not fun. Like it's like maybe root 2 times wider, and you get, so it's like a robustness to optional stopping and continuation versus width trade-off. Okay, so if you are committed to a single time ahead of time, a fixed n, then go ahead and construct your confidence interval. But I think it's actually impractical in many settings to commit to a fixed sample size and promise that when you reach that fixed sample size and your confidence interval looks close to what you would like, you feel tempted to say, let me just collect a little bit more data. But sorry, you can't. Like once you have committed to a fixed sample size rule, you simply cannot switch to saying, okay, let me collect some more data, things like that. So in some sense, the confidence sequence is a safer option, but you pay a price for it. Ultimately, the data scientist needs to make that trade-off. There is some kind of intermediate between these. There are these kind of group sequential methods and so on, which maybe are some kind of intermediate between confidence intervals and confidence sequences. So you should think of a confidence sequence as a group sequential method without a final stopping time, with infinitely many peaks, something of that kind. Yeah.
Okay. For different experiments, do you assume their p-values are independent? I think that's
Yeah,
the
so
last part.
that's a great question. That's a question about this slide, and I guess the answer is different papers make different assumptions. So maybe I should I'll go to this one. Um, so in the original papers, I think independence or conditional independence was assumed, like somehow conditioned on the past. In some sense, the only dependence is really through alpha. Like the alpha of a future experiment depends on the alpha of the past experiments, but somehow the p-values or e-values are still valid conditional on the past. So most of these papers assume some kind of independence, but the last one in the EBH, the online EBH, that does not assume independence. That can handle arbitrary dependence between the hypotheses. And there are other intermediate solutions in which there's local dependence, meaning dependence amongst a few experiments. And so I've omitted that. There's a Journal of Machine Learning research paper called Asynchronous Testing of Multiple Hypotheses, in which some intermediate notion of dependence between full independence and full arbitrary dependence, just locally in time there's dependence. So there's variants of these there. So there is a literature which addresses variants.
Yeah, we have a follow-up in the QA, follow-up to the cross-fitting question.
Yep.
Can we split multiple times and combine information from different splits?
Yeah, absolutely. So there's many variants of cross-fitting. So let me go back to the cross-fitting slide, since there's been a couple of questions about it. So yeah, there's nothing that stops you from, instead of doing 2 splits, doing 10 splits and kind of learning from 9/10 of the data, evaluating on a 10th, and then repeating over those. This is the simplest thing to describe in a talk, but you can definitely, in terms of both validity and efficiency, 5-fold or 10-fold versions might be better options. Yes.
Okay, great. I think that's almost all the questions, and I would like to finally thanks Professor Ramdas for this nice talk and for answering all the questions. And thanks to all the audience. We have a large body of the audience today. And as we said, the recording will be available on NIST website and also YouTube channel. And if for audience who want slides, feel free to reach out to us, and we'll be happy to share. All right. Thank you very much.
Thank you very much.
Thank you. Bye, Ramdas.
Bye-bye.